computer. Okay. Hi, good morning. I'm Jason Cottrell, founder and CEO of RCAM Technologies. With me today are two key project team members, Dr. Marcus Vernley, Assistant VP at WSP, and Dr. Phil Barutha, Assistant Professor at the University of Nebraska-Lincoln. Today, we're going to discuss our recent progress on phase 2 of our low-cost concrete support structure project, which is funded by the National Offshore Wind R&D Consortium. Here's a list of the project team members. The team is led by RCAM Technologies. We're a growing startup with offices in LA, Colorado, and Scotland. We're dedicated to developing renewable energy solutions for wind, wave, and energy storage technologies. We're fortunate to have the support of 8 additional team members, including WSP USA, University of Nebraska-Lincoln, NETSCO, who's a marine architect and engineering firm, the National Renewable Energy Labs, Kathy, who is a geotechnical engineering firm. And then we have the support of several subject matter experts, including Kiewit, Tufts, and the University of Delaware, for providing information and advice on transportation, logistics, and construction. We're also very fortunate and appreciative to have Equinor, Shell, Kiewit, the Department of Energy, and Maryland as project advisors. Also, we have cost share from Maryland and Colorado, Department of Economic Development, and the International Trade. So RCAM's products are primarily focused on using 3D printing technologies with concrete to manufacture low-cost support structure solutions, manufactured on-site and in U.S. ports. Our vision for marine energy is to use these automated technologies at port locations domestically and abroad to manufacture a variety of components for fixed and floating wind, as well as other marine renewable energy storage technologies. We discussed this vision in our presentation in the 2020 NOWRDC Symposium, which is still available on their website, or you can learn more about this vision and how it fits with what we're doing today at our YouTube channel, which is listed here, or you can go to our website at rcamtechnologies.com. But in general, the idea is that we want to manufacture these technologies in ports and domestic locations, thereby bringing domestic jobs and benefits and new design features to the offshore wind and benefiting disadvantaged communities around the port locations. The focus today, however, is on our fixed bottom foundation solution for the offshore wind market. As is broadly known, the U.S. is targeting to install about 30 gigawatts of offshore wind by 2030, nearly all of which will be on fixed bottom foundations. The majority of turbines will be installed on monopiles, which are essentially large diameter steel piles, 30 to 40 meters in, feet in diameter, that are hammered into the seabed. However, the steel monopiles and also the somewhat common steel jacket alternatives here face numerous challenges in the US. One of the primary challenges is the availability of the East Coast heavy steel construction supply chain for manufacturing the jackets and monopiles regionally on the East Coast. Also, the absence of a US flagged monopile installation vessel or wind turbine installation vessels is also quite problematic at the moment. And the noise created when hammering the monopiles into the seabed faces a challenge that needs to be mitigated. So our solution is a modular concrete hybrid foundation that can be wet towed to the installation site. Sometimes that's referred to as a hybrid wind turbine foundation. It's then lowered to the seafloor and anchored to the seafloor using nearly silent suction buckets. Here's an artist rendition of one of our foundation concepts that we considered in a project and a quick overview of the project scope. The project scope has 2 phases. Phase 1 is included, which has recently been completed, a conceptual design and feasibility study. And in phase 2, which we'll be focusing on today, includes the preliminary design and commercialization activities, as well as some analyses on manufacturing and assembly. So the solution has several key innovations, which are summarized here. The first one, of course, is the use of both automated and conventional manufacturing in US ports. So that's 3D concrete printing, as well as conventional pre-casting concrete construction, otherwise sometimes known as segmental construction. We use both of these technologies for different components on the foundation as shown here. The second key innovation is the ability to tow the turbine, either fully assembled or partially assembled, to the installation site. That uses the third and fourth innovations, which are integrated buoyancy chambers into the leg to help provide that buoyancy during the wet tow installation, as well as a supplemental buoyancy system, which is not shown here on this slide. And also telescoping suction buckets, which are then used to anchor the foundation to the seafloor. So here's a quick snapshot of the Gantt chart. The key is that we've progressed through phase 1, which is abbreviated here, and are wrapping up this project this calendar year. So before we dive deeper into phase 2, wanted to just give a quick recap of what we concluded from phase 1. Most importantly, we concluded that the concept is feasible. It does indeed provide a heavy lift vessel alternative. And also, the production rate targets can be met with the existing supply chain that we have available in numerous US East Coast ports. And finally, the LCOE is competitive with monopile solutions. In phase 2, as will be discussed further by Marcus and Phil, we have made progress on the preliminary design and are nearly finished with that, and developed the detailed assembly and launching process for the foundation. So with that, I'll turn it over to Marcus.
Thank you, Jason, and thank you to the audience for listening to this video. I'm Marcus Wörli. I'm an Assistant Vice President from WSP. I'm working for the Maritime Group. I've been working there for 25 years of experience in concrete floating construction and wind turbines. WSP is a large multidisciplinary engineering company with about 50,000 people worldwide. In this preliminary design, I just want to quickly go through the design criteria that are mostly driving some of those design components, and then look how would we build that today with a conventional construction methodology, and then what kind of changes would be made towards a 3D construction. Next slide, please. So here quickly, the design for submersion. We have about 4 different typical phases. One is, of course, the float out and this positioning the structure above its installation site. And then the legs, they are acting as buoyancy body themselves with additional buoyancy that is not shown right now. And for submersion, you would start to submerge partially to fill the legs partially with water, and you see that with chamber 1, the first one, to a draft of about 14 meters, and then the second chamber 2 to a draft of about 34 meters, at which point you will be probably touching the seafloor, which is about 50 meters below the water line. And then you start to penetrate the seafloor with the suction buckets, and you fill the shaft with water, and it is installed. That happens, of course, with a jacking system to guide it through the instability of going through the water line. Next slide, please. So this is how the leg cross section or the structure would look for if it is built conventionally. We would use a flat plating for easy construction. It can be built in a horizontal or as a segmental construction, which Phil is going to get farther into. And it's post tensioning in 2 directions so that you can take the hydrostatic pressure and the operational loads once the turbine is installed, and you build it with segmental construction. Next slide. Now, if we're thinking 3D concrete printing, then we want to build that same leg a little bit differently. For once, we want to optimize the shape and the wall thicknesses. Now, since we now can print more complex shapes and sizes, we take the advantage of printing voids and optimize the structure towards post-tensioning so that we can reduce the amount of reinforcement needed within the printing process. And then we optimize the structure or the structural components thereof so that they are optimized for the printing direction of the printer. And complex inserts like post-tensioning hardware could potentially be inlaid as part of a precast concrete elements, or they could be installed in voids which are then filled with cast-in-place concrete. So on the very left side, you see the concrete outline, which has now a arched top slab, and it has those slanted walls at the bottom to support the side walls a little bit, and that gives these additional voids as well. And that is a easier or a better shape of the cross section to take the high hydrostatic pressure. And the post tension, the picture right to the right, shows now that the post tension tendons are pulled all the way over the top of the structure in transverse direction, and you have anchors, post tensioning anchors, that are difficult to install and needs a lot of detail just only on two sides of the structure, which you then can accommodate with those inlays. Next slide. So the structure, as Jason already mentioned, is then segmented into those individual components that you can still handle them. And then the construction industry is going to decide what is best, what construction methodology is best being done. So if you look at the 3D concrete printing, we are seeing, let's say, the middle section of the beam. One is with and one is without a transverse diaphragm. You see that to your right, that you would probably lay that on its side, 90-degree side, so that you can start printing it layer by layer vertically. And then you would put in a scaffolding and formwork for the intermediate diaphragm and can continue printing if it is a segment with a diaphragm. Similarly, on the left, you see, we call that the well. That is where the suction, the telescoping suction buckets are housed. You would also print that vertically directly and then join that with those beam elements. And next slide, please. The suction buckets themselves, they could be printed. The cylindrical portion could be printed because it only has mostly post-tensioning and post-tensioning ducts in there and some minimum reinforcement that will have to be included in the printing process. And then the top lid, as I call it, has a big complex actually ring beam with post-tensioning anchors. That's where all the post-tensioning anchors are of this structure. And then it houses a steel dome, which you can directly, with cast in place, place the concrete on top. So it's a fairly simple construction and assembly method. The whole the whole suction bucket has to be designed for the installation, particularly the extraction pressure, which is then a lot of internal pressure that has to be taken. So that's why there's a lot of post-tensioning in it. Next slide, please. So the post-tensioning is arranged in a helical pattern. That way we can just keep post-tensioning anchors on the top and nothing on the side or on the bottom. And that is then a shape that we can actually post-tension and also keep the wall sizes to a minimum size and reduce the reinforcement. And again, optimize the entire this component for 3D printing, layering construction. Next slide, please.
Okay, so now we'll turn it over to Phil, who will speak about the assembly concepts and estimates of production rate and cost.
Thank you, Jason and Marcus. I'm Phil Bruth. I'm an assistant professor at University of Nebraska-Lincoln, representing the team in the construction programs of the College of Engineering here at the university. Next slide, please, Jason. I first want to talk about our main objectives for our assembly process and cost estimate development for the project. Really, our primary objective was to find a technically feasible conceptual assembly process for a 15 megawatt offshore wind turbine, following primary manufacturing processes. We found some very good outcomes of our analysis with our meeting our first couple of objectives. Our first main objective was utilize the existing concrete supply chain in the eastern United States with 100% domestic content. That was a good result of our project, as well as developing a process with the flexibility that can be generalized across all of the eastern US. And there's some potential with leveraging some economies of scale and some advanced construction methods. We feel like there's an opportunity to reduce some costs and production schedule to improve the overall LCOE as well with this design concept. Next slide, please, Jason. So in an attempt to realistically forecast cost, we used existing port locations on the East Coast to estimate our fabrication and assembly cost, as well as develop our process. Here, this is illustrating our various different locations along the supply chain of our assembly process. You can see our final installation site off the shore of Long Island in New York. But tracking all the way back in the process is our concrete fabrication site, which for our analysis, our case study site is the South Brooklyn Marine Terminal in New York. And following fabrication of our concrete foundations, they will be towed via the existing waterway to our turbine marshaling and assembly site, where we will be receiving our turbine components. And the final installation of the turbine will be mounted on our foundation, our tripod foundation, and then ultimately transported to the installation site there shown on this drawing. And that was the basis of our analysis. Next slide, please, Jason. So this illustrates our concrete fabrication assembly process that on the South Brooklyn Terminal site in Brooklyn, New York. Again, this is the tripod concept that Jason and Marcus were describing. So to maximize or optimize the amount of cost and time to fabricate this foundation, we've developed an assembly manufacturing process here, assembly line manufacturing process. Each of those lines illustrate a match casting process. We're using conventional methods for our baseline process, conventional segmental concrete construction methods for our baseline process. Each of those lines would be one leg of the tripod. And our assembly process is casting each of these elements on site for both the tripod as well as our shaft. You can see our vertical shaft extending up from the tripod location that are all assembled, both fabricated and assembled on site. And you can see the various different heavy lift equipment that will be utilized for this process for these very large structures that will be fabricated at that port facility. Next slide, please. And this is just showing the layout or preliminary layout of this fabrication site at the South Brooklyn Terminal. This is an 80-acre site in total, and you can see we're able to make our manufacturing process fit within the footprint of this existing port facility. Next slide, please. And this slide is representing our marshaling and assembly at the existing State Pier Port facility in New South London, Connecticut. You can see where the plan is to receive our turbine components delivered via barge, mostly to this location, offloaded on this site, and finally installed on our fixed bottom tripod foundation as one completely assembled unit, and then hauled and transported to its final location site. So this is depicting our various different turbine components that are staged, prepared for final assembly to be towed out to its final installation. Jason, next slide. And then finally, we were able to put together a preliminary cost estimate. This cost estimate is based on 67 total turbine site. of our 15 megawatt reference turbine. Our comparison, our cost comparator is to the monopile system, monopile foundation system. What we're able to find is our costs for our tripod are competitive. However, the monopile system may have some technically technical feasibility challenging elements that may make it more difficult to install at the 50 to 60 meter depth. So the estimate for the monopile, I think, is still yet to be verified and validated. The comparator. In addition, we also feel like there are some cost savings that will be realized with the turbine assembly and installation at sea that's not reflected in this cost comparison, side-by-side comparison. And we also feel there's potential for labor production rate increases in the future, is anticipated with more mass deployment of this system, as well as if automated equipment or more automated formwork systems in 3D concrete printing are being explored to reduce overall labor costs as well. So feel there's some opportunity for some cost savings in this area. Thank you, Jason.
Okay, so this is the last slide here. We're pretty much out of time. So in general, what's coming up next, we'll be focusing on the commercialization, updating CapEx and LCOE estimates. The regional economic benefits analysis will help us compare the economic benefits compared to steel monopiles, updating our risk assessment and planning commercialization, testing and certification activities, as well as a comprehensive stakeholder workshop coming up at the end of the year, and a quite long 400-page final report. So with that, we thank NOWRDC for their support and the cost sharing partners. And of course, the entire offshore wind industry seems to be hiring right now, and RCAM is no exception. So we're looking for structural engineers and other folks. Please contact us and don't hesitate to reach out if you or someone you know is interested in working on these cutting edge technologies. So thank you very much. Enjoy the rest of the conference.